I was just introducing the outline of the presentation. So I'm gonna talk a little bit about what is macroseismology, so in general, and then of course I will focus on the ESI scale. In particular, I will deal with some of the concepts or ideas specifically related to the ESI scale. And I should just anticipate here, which it is a macroseismic scale dealing only with environmental effects. I will present the state of the art, and I have some good news to share with you all on this point. And I will show you some examples of published paper and case histories analyzed using the ESI scale. And finally, my, let's say, my takes on what should be expected for the next future. Okay, so macroseismology in general is the analysis, the classification of earthquake effects on humans, buildings, and nature. So it is done by applying intensity scales, which usually have 12 degrees from degree 1, which is basically an earthquake felt only by very detailed instruments, up to degrees 12, which is basically total destruction of buildings, infrastructures, every human activity, and also huge effects on nature. So basically, the three reference that we deal with are the effects on humans. And in this case, humans basically saturate at grade around intensity 6, which means that starting from intensity 6, people get panicked. So it is not possible to assess in a good way the higher degrees. So we should move to buildings or in general objects. And in this case, or better, this is the main topic or the core of most of intensity scale. In particular, in Italy, we have the Mercalli-Cancani-Seeberg. In many other parts of the world, there is the modified Mercalli scale. In Eastern Europe, the Medvedev-Sponhauer-Karnik scale, MSK, is much more used. And in the last, I would say, 20 to 25 years, the European macroseismic scale has been introduced. And the peculiar characteristic of this EMS scale is that it includes a definition of building styles. So while in the former intensity scales, they are basically devoted toward the brick or masonry buildings, in the EMS also reinforced concrete or more modern building techniques have been taken into account. And finally, we have the effects on nature, so on the natural environment. And this is a little bit trickier, let's say, because in the current practice, for instance, in the EMS scale, such natural effects are considered not really reliable because they are supposed to do not provide a statistically sound sample. But, well, this is an opinion, let's say, or this is a position in the scientific community. And the ESI scale instead is focused only on these environmental effects. So yeah, it is called also ESI-07 because it was introduced in 2007, as we will see in a minute. The main characteristic is that this scale is based only on natural effects. As most of the other intensity scale, it is a structured, it is a classification, first of all, and it has 12 degrees. The main point I want to stress is that this scale does not aim at replacing the former macroseismic scale that I described before, but the general aim is to provide independent information. So if we already have good information coming from another intensity scale, then focusing only on the natural environment can add some information or can confirm what we already have in our hands. But we will see there are some peculiar cases where basically natural effects are the only way to go. So in this specific case, we believe that the ESI scale performs better than other, let's say, traditional or other scales, which are mainly focused on building, damage on building. I put here the screenshot of here to the right, the let's say the guidelines, the paper that proposed the ESI scale. So it includes a description of the scale, a description of how to use it and when to use it. While the paper I put here at the bottom of the slide is, let's say, a sort of review, so is assessing again few years after the introduction of the ESI scale its main purpose and is target mainly toward the hazard community or people dealing with hazard. Okay, what else? I now try to follow the evolution or the journey of the ESI scale. As I mentioned at the very beginning, this activity and this macroseismic scale is has been conceived and developed within INQUA. So the first idea came more than 20 years ago now, during the 15th Congress in South Africa. So at that moment, the idea that it was good to start building an intensity scale based only on nature was first assessed. So the process began, let's say, and a preliminary version of the ESI scale was published or was proposed to the public in 2003 in the next INQUA Congress. At that point, a specific INQUA project was started, let's say. So in these few years, from 2004 to 2007, a working project, a working group was trying to analyze a number of earthquakes that had occurred in the past and to apply the newly proposed scale in order to assess if it is reliable, if results are reliable, and if it can be applied in different, let's say, seismotectonic setting or geographic climatic setting. So basically, after these years of work, in 2007, the scale was officially published and ratified by the INQUA authorities. And since then, many earthquakes were analyzed, many case histories were analyzed using this specific intensity scale. So which is the structure of the scale? Well, this infographic basically contains everything we need to know. So in the vertical axis to the left, we can see the intensity degrees. So from 1 to 12, moving from the top toward the bottom of the image, while on the horizontal axis at the top of the image, we can see the different type of earthquake environmental effects. There is basically a big distinction between primary effects to the left and secondary effects to the right. So primary effects are those directly connected to the seismogenic source. I have a couple of pictures in the next slide. While secondary effects, let's say, are those connected to ground shaking. So they include a number of different processes and phenomena. The important point is that the ESI scale tries to quantify or to describe the dimension of each type of effects for each intensity degree. So for instance, in the case of primary surface rupture, the first column to the left, we can measure offset and length, and we have different categories, different units, different measures for each intensity degree. So it is there is a paved way in order to assess the proper intensity level. This is, I focus on this point because often one of the criticisms that it has been done to the natural effects is that they are not reliable because they are too variable. They are not. They do not repeat in the same way. But this framework of the intensity ESI scale allows, or we hope it allows to classify in a consistent and systematic way all these kind of effects. So let's start digging a little bit more from the primary effects. As I mentioned a minute ago, they are related to the seismogenic source. So the main type of effects is primary surface rupture, ground breaking, and the intensity here is assessed based on length and width of these tectonic ruptures. Tectonic primary effects start to be evident at intensity around 7 to 8. So they are not present at the lower intensity degrees. Actually, if we have a blind source, so no primary faulting, nevertheless, we can still evaluate an ESI intensity scale, an ESI intensity degree based on the amount of tectonic uplift or subsidence, for instance, as measured using remote satellite data. Here I put a couple of examples of primary ruptures following the central Italy seismic sequence. So we have the fault plane, the bedrock fault plane, and at the base we have the offset related to a seismic sequence actually occurred in 2016. Okay, let's move to secondary effects. I would say these are much more widespread and affect a much wider region. They encompass different types of effects. So we may have ground cracks, and here we can measure again the length or how wide they are, how deep, the offset, and so on. Then we may have slope movements, different type of slope movements, and usually what is considered is the volume to assess, to assign an intensity degree. We may have liquefaction processes, and here the metrics, the quantitative estimation is based on the dimension of sand volcanoes, for instance, or the length, again, of liquefaction phenomena. And then we may have anomalous wave, tsunamis, and so on. And here the intensity is assessed based on the run-up or the dimension, again, of the anomalous wave. There are few additional secondary effects like hydrogeological anomalies, like variation in the discharge of springs or appearance or disappearance of new springs, changes in turbidity, and so on. So all these type of effects are described in the intensity scale guideline, so one can look at the description and assign the precise intensity degree. Another important point I want to briefly mention is that in the ESI scale structure, there is a clear distinction between site and locality. Actually, this is not peculiar of this scale, but all macroseismic scale has these have this hierarchic structure, let's say. So the site is any place where a single effect has occurred and has been observed. And it is recommended that the compilation of earthquake effects should be done at the site level. And the locality instead is let's say a generalization, so it may include one or more sites. For instance, I put here to the right a picture, an helicopter picture of landslides triggered by the Hokkaido, Japan event in 2018. So site should be each single landslides. While locality can encompass a number of landslides. And anyway, both sites and localities are point values. So this is important for the subsequent steps, let's say. Another important point, which is in this case really peculiar of the ESI scale, is the difference between local intensity and epicentral intensity, in the sense that local intensity is what I described a minute ago, so is the intensity assigned for a locality, is a point value, while epicentral intensity is a different kind of beast, because it's not a point, it's a region. Is based on linear or areal feature, such as the length of surface rupture or the dimension of the region affected by secondary effects. And this is quite peculiar of this intensity scale, because this possibility is actually not included in other scales based mainly on damage to buildings or to the built environment. So yeah, it's important to stress this point, because the name, the definition is different, even if we call both of them epicentral intensity. Okay, now I skip to the state of the art. Here, as I mentioned, I have a breaking news. I'm still high on this news because my paper dealing with a collection of all the case histories that have been analyzed using the ESI scale have been accepted just 2 days ago. So what we did is to collect information on 157 earthquakes, which have been analyzed using this intensity scale. We built a data set with the information concerning the, let's say, seismological aspect, so magnitude, earthquake kinematic, length of surface ruptures, and so on. We then put a field related to the maximum and epicentral ESI intensity, the eventual availability of intensity assessed using other scales, and we compared these values in order to assess if systematic differences were present. So this is a way to also assess if the ESI scale is reliable or not. And also we developed empirical scaling relation among the epicentral intensity and magnitude length of primary surface rupture or affected area. I put here a quotation from the reviews we got, just to be fair and honest toward the audience, and in particular toward the early career people that may listen this talk, because, well, the ESI scale is far from perfect. It doesn't want to replace other scales, and still a part of the scientific community is not fully convinced about the validity or the reliability of the scale. So I personally believe it is our duty to try to provide them the grounds on which they can base an informed, let's say, opinion. So what we did in this paper is, as I mentioned, step one is a literature review. So we collected all the papers and all the, let's say, case histories analyzed using this scale, and we filled a big spreadsheet with this field listed on the right of the slide. So this is a way to, of course, we are simplifying things, we are selecting information, so it can be, I mean, it's a subjective choice which field to include in our data set. We believe to have caught at least the most important aspects or the most important parameters on which perform a comparison. So this is a map showing the location of the earthquakes that were analyzed using this scale. As you can see, they are quite widespread on a global scale. There are places much more intensively studied, let's say, such as Southern Europe, or let's say the Mediterranean region. And there are some other places that actually have never been investigated using this scale. So what we did is, as I mentioned, to fill a field using with the maximum intensity with any other scale, and the ESI epicentral intensity. So basically all the points within the shaded area in these graphs basically show a good agreement between different intensity scales, and we are happy about that. Another point that maybe I should have mentioned earlier is that intensity is a classification. So let's say we move, for instance, from degree 6 to 7 to 8. So it's not a continuous variable, it's step by step. So we should bear this characteristic in mind when we perform the regressions or some numerical analysis and statistical analysis of the data. So basically, we see that there is overall a good agreement between effects on nature and other effects measured using other intensity scales. So we also developed some scaling relations, and in all these graphs there is the epicentral intensity on the y-axis, and we realize a numerical regression between moment magnitude, the length of primary surface structure, and the area affected by earthquake environmental effects. So, well, we see almost everywhere a good scaling relation. So, as expected, basically, the epicentral intensity gets higher with a bigger magnitude, longer primary ruptures, and a bigger affected area. We, of course, also provide the numerical coefficient and standard deviation for the regressions. So let's see what we gained from our literature review. I'm showing here some examples that were published during the years on the use of the ESI scale, and I will comment on basically what the scientific community told us about the strength and the limitation of the applications of the ESI scale. So let's say the basic approach or the standard approach is to go to the field to collect information on environmental effects and to classify them, so assigning an intensity degree. Many papers so provide the position, the location of points with a given intensity. Many papers also draw isoseismals, like in this case, which is referring to the 2008 Andravida Greece earthquake. So this is a very common output, a map or a table with the coordinates of localities and the isoseismal lines. Another very common output is to compare here with a different degree of, I mean, someone more qualitative, someone more in a quantitative way, to compare the output of the ESI scale with other macroseismic scales, and in particular with the damage to the building, to buildings and infrastructures. So in the scientific community, many people do this kind of comparison. Another type of approach is instead based on, let's say, a grid. So the territory is divided into cells with a regular dimension, and an intensity is assigned to each cell. I put here an example from Japan, a famous, let's say, a devastating event in Japan. This approach is less used, but I believe it is just due to the quality of input data, and I believe this approach will become more and more used. This approach is particularly used in the case of slope movements, because it is, let's say, quite easy, at least in some climate setting, to map slope movements based on satellite imagery. So it is also quite straightforward to, for instance, count the number of landslides per cell, or define the area or volume of each landslides. So I believe, as I said, that this approach will gain popularity in the next years, let's say. Another interesting application in this case is mainly developed by the Spanish group of people working on the ESI scale, and they are basically applying the Shakemap procedure or algorithm using natural environmental effects. So the result is very similar to the classic Shakemaps, for instance, produced by the USGS, but the difference is that here they refer only to environmental effects, so they can also compare intensity with the PGA, so with the parameters or metrics which may have an engineering importance. Another quite interesting application that is starting to be more and more used is the development of attenuation relations. So basically, intensity attenuates with the distance from the epicenter or hypocenter, and intensity prediction equations are one of the key ingredients for hazard assessment. Well, there are plenty of such prediction equations based on let's say, the Mercalli type intensity scales. And now some attempts have been tried by using the ESI scale. In the image, there is one of such attempt related to the South American subduction earthquakes, and the comparison with the Italian Apennines. Well, I put it here, this specific relation, because they have been the first to have been produced. But again, I believe that in the future, similar research will be made in a number of different seismotectonic and geographic settings. So coming toward an overview of the presentation, which are the strengths of the ESI scale, so where it is best applied. One of the interesting points is that natural effects, or let's say nature is everywhere, so natural effects does not depend on the distribution of buildings or of infrastructures. And they also do not depend on building techniques. So the ESI scale is, I believe, the best way to go in remote regions, or in poorly inhabited regions, or in regions which are difficult to access. Another important point that has been highlighted in the literature is that natural effects seem to be more consistent through time. I mean, if we use damage on buildings, there is a strong influence of the building technique. And for instance, buildings, modern buildings are different from historical buildings. This is not true for environmental effects. Of course, there is a geographic difference. For instance, in some sites, we may have amplification phenomena, but still at the same site, the local setting does not change that much through time. So this means that this kind of scale, or in general, the analysis of natural effects, can be applied to earthquakes that occurred in pre-instrumental, instrumental times, and even in the future. So one of the outcome is that natural environmental effects provides independent data with respect to traditional scales. In many cases, this independent data may confirm what I've already achieved. In some situations, that they can provide additional information, like the first point of the slide. So when there is not that many buildings, for instance. It's fair to include also a slide on the challenges and the problems related to the analysis of natural effects. Well, the first point relates not only to natural effects, but to, I would say, every observational science, in the sense that the quality of input data heavily affects the reliability of the results. So there is an issue related with the completeness of the input data. And of course, if we analyze an earthquake that occurs today is different, or the amount of information should be higher than an earthquake occurred, let's say, 200 years ago. When we speak about geological effects, also we have to consider the preservation potential. So basically, this is variable and depends on the type of effect, let's say primary faulting versus liquefaction or whatever, and also on the local geomorphologic setting. So each type of effect can be preserved in the geological record for a different amount of time, and the most subtle effects can be erased quite quickly from the geological record. Another point that have been pointed out in the literature is that primary surface faulting can be very complex in the shape or in the amount of faulting. And so here we have an issue related to the, if we think in a paleoseismic perspective. So how can one be sure that the surface faulting can be attributed to a single event or to a seismic sequence, or how, for instance, in the last year, we have seen that strong earthquakes usually involve multi-fault ruptures. So if we bring this back in a paleoseismological perspective, which are the implications? So this is still an open question. Another point is that the estimation of the total area affected by secondary effects can be made using different methodological approaches, and I think there's not still a real a single approach. So results may be affected by methodological choices. And the last point of the slide is that some of the or some peculiar effects, for instance, permafrost regions, or some effects in very peculiar local geomorphological settings, have not been described in an adequate way in the guidelines. So maybe some additional description could be worth a try. So the last slide is on what's next. So this actually is my personal take, so don't take it for granted. These are the research line I think will be pursued in the future, in the near future. So the first one is that recent events or the resolution of data related to recent event is much, much higher than past event. So probably new metrics will be exploited or explored, like the dimension of the area deformed observed by interferometric studies. As I mentioned before, the grid approach, I think, will be more applied, in particular for slope movements. Another avenue may be the analysis of hydrogeochemical variations, so the water, the groundwater system. Another point, which is not only dealing with the natural effects, but on earthquake effects in general, is the analysis of seismic sequence and the cumulative damage. So the idea is to try to disentangle the effects related to, for instance, the main shock and the aftershocks within a seismic sequence. What I presented you before were among the first empirical regressions. So in this case, the addition of new case histories will allow to derive more precise, or maybe to derive regression specific for a given seismotectonic setting. And the last one is something I'm not expert on, but I bet, if I have to bet, the environmental effects can be applied in planetary geology, and here they are the only way to assess earthquake effects, not earthquake, but seismic events effects in planetary science. So that's all from my side. I will take any question from the audience, and I hope to see you all in Rome next year at the INQUA Congress.